started. The Grignard example, we ended with this, right? Looking at Grignard, vaguely. What's your nucleophile in the Grignard example? As a hint for all of these, if you take a look in the upper left-hand corner, also got it kind of categorized. So we're looking at the carbon. One of the things that's easiest to do with the Grignard reagents is to lose carbons. So make sure when you go through and run a reaction, you're being very careful with your carbon count and make sure that balances all the way out. Okay. Would we expect it to be more effective under acidic or basic conditions? Grignards have two primary sources of reactivity. They can act as nucleophiles and they can act as Bronsted-Lowry bases. Would we expect this reaction to work well if we made it acidic? What would the Grignard reagent act as? A base. Accepts the hydrogen, we no longer have a carbon nucleophile. Would we expect this reaction to work if it was under acidic conditions? No, lost the nucleophile. Okay, so we're looking at basic conditions for all Grignard reactions. To react completely, we've got two carbonyls, so we would have two potential reactive sites. So if we want our Grignard reagent to react at both carbonyls, we would need at least two equivalents. Why do we need three equivalents? What functional group do we have here? I know it's Monday. We have an aldehyde. What functional group do we have in the other corner? It's an ester. Why do we need three equivalents to react completely with all the carbonyls? Esters have some interesting chemistry. That oxygen is a really good leaving group. So we can have our carbon nucleophile attack the carbonyl, and we can kick out the leaving group in our oxygen. We've now generated what functional group? I know it's not drawn up there. Let's see if you can predict it out. Kicked out the leaving group of the oxygen at the same time that we formed a carbon bond. Carbon-carbon bond. What was that? We'd now have a ketone. As far as reactivity, which reacts faster, the ketone or the ester? Ketone reacts faster than the ester. So our ketone would then react a second time with our third equivalent, if we will, with our Grignard reagent. And it would continue to propagate out until all of our ketone was gone, and then we'd continue to react with our ester until all of the ester was gone. So we're looking at three equivalents. So far as reversibility goes, that's a little bit of a harder question to ask until we actually look at the reaction. So remember, if I've got the reaction up here or not. Looks like I do. Why would there be two steps? Why do we do this with the Grignard reagent first and then add the dilute acid? What's the other option? Add it all at once. Is that an acidic reaction or a basic reaction if we add it all at once? Neutral because the acid reacts with the base. Do we have a nucleophile if the acid reacts with our base? Nope. So why are there two steps? We need to make sure that that acid-base reaction doesn't occur, that we do our nucleophile-electrophile reaction first. If we looked at the overall Grignard reaction, we could go through and look at each of those steps. Can't say mechanistically this is the nicest because we've got a couple different mechanisms or reactions all happening at the same time. And the order is all sorts of awful. But if we react with that ester, you'll notice that we do have that leaving group with our oxygen. Okay, our oxygen can take the electrons and shift outwards. And then we've got the other steps of our reaction with our Grignard reagent reacting with each of those other carbonyls. Okay. And then we'd follow that all up with the acidification. So it looks like one big god-awful mess. Okay, which is fine. It's okay. Questions about anything with the Grignard reactions? They should be fairly confident with those now. We'll accept it and move on. The other one that you could see would be the cyanohydrin. I didn't show the acetylide reaction. Kind of regret showing that, not showing that in the slide, but remember we can form, and in our group, we can form another very similar reagent to the cyanohydrin with the acetylide ion. Where we can pull off that hydrogen, put in that negative charge. How do we get that reaction to work? We form the acetylide from acetylene. What did the acetylene act as? What did it do to go from part one, or reactant, to product? What changed about its structure? Lost to hydrogen. What kind of species donates hydrogens? Acids. What did we react this with? What do all acids react with? I know. Come on. Bases. What base do we react with our acetylene? That's a trickier question. Sodium hydroxide? There's a reason I'm not writing.
Isn't sodium amide?
We need sodium amide to be able to deprotonate. Sodium hydroxide is not a strong enough base to actually be able to remove that hydrogen. Okay? Cyanide is a little bit easier to get a hold of, though probably not for good reasons. So we can generate a similarly negative carbon to have a carbon nucleophile, and while that is nice, synthetically we put on the cyanide group. The big issue comes into play with that species right there, known as hydrogen cyanide, also extremely, extremely toxic. I think we've talked about this a few times. If you smell almonds, it's usually a bad thing, okay? At least when you're working with these cyanide compounds, because that's their characteristic scent is cyanide, okay? Or is almonds. So one of the huge disadvantages with these reagents is that extreme toxicity. Okay? However, as toxic as it may be, it does actually have a reasonable amount of synthetic options to it, because we now have this alcohol and we also have this nitrogen that we could then convert around. So there's two possible products we could generate from this. Okay? How do we get those two possible products? You might be able to tell there's boxes. What changed to go in that first reaction? To go from reactant to product number one. What changed?
Added 2 hydrogens.
We added 2 hydrogens? You might be right as far as counting that out. May just be a nomenclature thing. What 2 hydrogens did you add?
The amide.
So just those?
Oh, and
Yeah, and the carbon. This is why I said it's might be a nomenclature thing, because we added 2 equivalents of hydrogen. Okay, so we added H2. Okay, how could we go through and do that? Okay, we could reduce it. We know all sorts of reducing agents. The one the textbook was suggesting here is the lithium aluminum hydride to go through and help reduce that. More than likely, we'd want to choose that over, say, H2 and palladium or H2 and platinum, because why? We're probably looking at a sizable amount of heat. Yeah, it's a good call. That's another big issue with the H2 and platinum or palladium reagent. That shouldn't be an issue. Big issue with that reagent is it's not specific. Okay? It can react with your alkenes as well, and your alkynes for that matter. So the lithium aluminum hydride is probably a better option because it will target these heteroatom multi-bonds. Okay? So we can get that NH2 now put onto your structure. How about in the next one? What changed? So we oxidized. to go through and get this one to work, and I would recommend that you try a mechanism for this, we're going to add just H3O plus and a little bit of heat. Why is just adding acid going to get this reaction to go? What's the acid going to react with? If we put a hydrogen on our nitrogen, what charge does it become? Positive. Does nitrogen want to be positive? No, what does it start to do? Take the electrons away from the carbon. So then the carbon becomes what charge? Positive. What can we do now? We can bring in the nucleophile of water. And we can do this a couple different times, okay, to go ahead and push all the way across to the carboxylic acid. Okay? So relatively simple reagent. You're going to get lots of acid-base steps in that mechanism. Okay? Again, I do highly recommend that you go through and give that reaction a shot because you're going to continue to see these types of mechanisms. Just a lot of acids and bases. Okay? And because I know we're already going to look at a bunch of others, I'm not going to draw it out. Questions about the cyanohydrin? Okay. This is a pretty big one, big name. You get the Wittig reaction. I was always kind of confused by it. Never really saw it as anything all that important. And it's also in kind of an odd section. We go through your cyanohydrin is what? Section 10. And the Wittig, oh, never mind, is also in section 10. Okay. So what's going on with the Wittig reaction? Okay, we're going to add a whole bunch more reagents to this, but in the process, we're still generating a carbon nucleophile. We're just going about generating that carbon nucleophile in kind of an odd fashion. Right? So ultimately, your Wittig reagent is the guy right in the middle there. Okay. We generate a negative charge on our carbon. We've got that carbanion with our lone pair. That can then act as your nucleophile. And we can go through a sequence of other mechanistic steps. And we end up kicking off a phosphorus oxide compound. And in the process, we end up trading our carbon for our oxygen. So it's kind of neat that we can get a couple of mechanistic steps to occur there to actually put on our carbon. So if we take a look at, we highlight our carbons. So the carbon from our Wittig reagent is actually the carbon that's now attached, okay, to our structure. So what we end up doing is completely swapping the oxygen for our carbon. Kind of neat. Okay. What if I wanted an R group out here? Just make that R. What would I have to do? When I go through to make the Wittig reagent, that just needs to be an R group. Okay? So this is very general. We don't have to have hydrogens there. We could have much larger structures coming off of that carbon to go through and generate our product. Okay? Any ideas on potential ways that we can make the Wittig reagent? Think we'll need an acid or a base? Probably need a base. Why a base? The carbon needs to become negative. Okay? There's really only one thing we can remove from carbon relatively easily to get it negative. It's going to be a hydrogen. Okay? So what we're going to end up having to use is a very strong base. Why can we get away with using a strong base in this case, but we couldn't if it was a straight alkane? The phosphorus is large enough that it can stabilize our anion long enough to actually allow the reaction to occur. So we end up activating our alkane, allowing this reaction or this reagent to form. Okay? Which atom is our nucleophile? The carbon, in fact, our orange carbon. Which atom is our electrophile? Our carbonyl carbon, which I can go ahead and circle now as our red carbon. So being able to identify those pieces can really help out. Okay? So let's take a closer look at the steps of our Wittig. The intermediate Wittig or the Wittig reagent is oftentimes called an Ylide, which I'm sure I'm brutally mispronouncing. Okay, so if we look at just that reagent, why is it something that we can actually make? And it comes back to the fact that that phosphorus has that positive charge because it has too many bonds. And so we can share the electron density between our carbon and our phosphorus. Okay, so that stabilizes that carbanion long enough, allowing it to form, but doesn't make it so stable that it doesn't then react. Okay, between these two structures, which one do you think is the predominant form, predominant Lewis structure? Okay, you say the right. Why? What's that?
Doesn't have formal charges.
We don't have any charges, and I like that thought. I agree with that too. Turns out we're wrong. Okay, why is the leftmost structure favored? Okay, it's kind of an odd explanation, but it's kind of neat in that same respect. What changed? Made that pi bond, right? How do we make a pi bond? All pi bonds are made the same way. Kind of. Moved a lone pair from what into what? Into, I like that last statement. You said something about orbitals. What orbitals? P orbitals. A pi bond is formed by the overlap of p orbitals. What if your p orbitals don't overlap? Can you get a pi bond? No. The only way we get a pi bond is if our p orbitals overlap. What's the big difference between carbon and phosphorus? Size. Phosphorus is relatively huge in comparison to carbon. What does that mean about your p orbitals? P orbitals on phosphorus end up being substantially larger and further away than the carbons. You don't get very good overlap between those orbitals. If you don't get very good overlap, what happens to the strength of that pi bond? It becomes incredibly weak, and we start to favor the charged species instead of the pi bond, our neutral one. Okay? So there's kind of a neat thing to consider and look at. How do we end up forming it? Okay, what we'll start with is triphenylphosphine. You will more commonly see that reagent written out as PH3. Okay. Why do we want phenols? Why do we want phenols? What are those phenols doing for us? Yeah, it's going to be kind of a steric effect. They're going to kind of block and help prevent that phosphorus from acting as that good of a nucleophile. So that later when we make our Ylide, that we can get the carbon to be our nucleophile and not have our phosphorus get involved in that. Okay? So that's one of the big reasons we need those phenyl rings. So what we're going to do is a standard what type of reaction in that first step? No, I was about to tell you the answer. What reaction occurred in our very first step? Nucleophilic attack. You can push that a little bit further. What type of reaction was it? Was it an addition reaction? It was a nucleophilic substitution. So SN, which mechanism? 1 or 2? How do you know it's 2? One step is one option. You could show all of our arrows happening in the same step. That's the same statement. Okay? So we're looking at an SN2 mechanism. So if we were going to write this out as far as what you would see in a reaction, you would probably see PH3 and CH3I written as step 1, okay, as a possibility. What happens in our next step? What type of reaction occurs in our next step of the reaction? Elimination is fair. I could accept that. Okay. It's not quite an elimination because it's only the first part of it. We never really formed the double bond, right? We've got the charged species. So we might call it an elimination step 1. I definitely like your other statement. What was your other statement as it could be? It's an acid-base reaction. What was the acid? The hydrogen. Our middle thing was our acid. What was the other guy? Definitely then had to be our base. Okay. Would we expect that species to act as a strong base? What do you think? The only one that's written as a base. Would we expect that one to act as a base?
Yes.
Why?
'Cause it has a little pair.
Negatively charged. Negatively charged is a good tip-off that we're looking at a base or a nucleophile. Okay. Would I expect it to be a strong base or a weak base? Is it stronger than OH minus or weaker? What's the difference? We're looking at OH minus, or let's just do O minus versus C minus. Which is the stronger base? Heard a bunch of people say O minus. Okay, so tell me why O minus is the stronger base. If you circled that, you're wrong, by the way. Why is O minus the stronger base, now that you know it's wrong? What's the idea? Electronegativity is your good comparison. Oxygen is more electronegative than carbon, which means it wants to hold its electrons. Which one's going to be more willing to share them? The carbon, because it's less electronegative, which means our stronger base, whoa, things popping up right and left, is our carbon. All right? So when we're looking at this species, we're looking at usually a very, very, very strong base. Okay? This type of species, let's see if I remember this correctly. Did I tell you guys earlier in the semester there was a woman at UCLA that caught on fire? It was that big hazard kind of thing because she wasn't using chemicals properly? Okay, well there was a issue in UCLA where a woman got caught on fire because the species that she was working with auto-ignites in air. That species happens to be this guy. Okay. We're not doing a lab with it. It is dangerous, don't get me wrong, but it's something if you know how to work with it, you're okay. You'll sometimes see it written out as butyl lithium. Why butyl lithium? There's 4 carbons. So we've got butyl lithium. You might also see Libut or something along those lines. Okay. That is a very, very strong base. We'll pull off that hydrogen off of our carbon. We now have the Ylide, which is temporarily stabilized by that p orbital overlap between our phosphorus and our carbon. And we now have our active nucleophile in the carbon. Okay. That now activated nucleophile can react with our electrophilic carbonyl carbon. We can go ahead and do that full-on substitution. Okay. So textbook broke down those individual slides for you. You can see your first attack or your first step of the reaction being your nucleophilic attack by the Ylide on the carbonyl carbon. That negative oxygen is now in very close proximity to that positively charged phosphorus, which is kind of an interesting thing. Okay. Most cases, we would say that step of the reaction would never occur. Okay. As a hint, which of these steps is most likely to be the slowest? How about the second step? Why is that second step the slowest? Why should you always be cautious to draw mechanistic arrows like that? Why do you not see it very, very often? It's true. It does make sense, and it's actually how this reaction works. It does self-react. It's an intramolecular reaction. Also, it's a favorite type of reaction for the ACS test. You'll see intramolecular cyclization reactions or decyclization reactions. Okay, why do we typically not see it though? Along those lines, take a look at the product. What do we have in the product of that step? We have a 4-membered ring, right? 1, 2, 3, 4. What's the issue with 4-membered rings?
Angle strain?
Yeah, we're getting massive amounts of angle strain on that. Okay? So it's not a particularly nice reaction to occur, but it is something that we can see as a natural product in some cases. The phosphorus is probably going to be one of your largest contributing factors to allowing this to occur. Why? What's special about the phosphorus? It's really, really big, which means we can open up those angles a little bit. Okay? And phosphorus will be able to share those electrons a little bit better. All right? So once we've formed that 4-membered ring, the oxygen can continue to share its electrons, and so what we end up seeing is an internal, technically electrocyclization reaction, I believe, because we're getting our electron transfers occurring backwards and forwards. The oxygen gives up its electrons to the phosphorus. The phosphorus then has too many electrons, so it can give up its electrons to the carbon, and we get our double bond. Okay, and we've done our exchange of electrons, and we now have our final product. Okay. It's a bit tricky of a reaction, primarily from what was sort of alluding to at the beginning. Okay, we might start with, might even get written out as something like CH. I do all the, oh crap, let's just draw it. You might see something like this, reacting with the first step, our triphenyl phosphorus, followed by our butyl lithium, followed by some carbonyl compound. Okay? So it can get kind of hidden in what's actually occurring. Okay? So there's two big things that's happening. Number one, we're making the carbon nucleophile, and that's, in this case, I'll go ahead and circle them. That's starting with our electron-deficient carbon. We need to have that good leaving group with an iodide. That can then react with our phosphorus in a substitution reaction. We can then follow that up with an acid-base reaction to remove that last hydrogen off of our carbon. And we now have our carbon nucleophile. Once we've generated the nucleophile, we can react it with pretty much anything we want. In this case, we're going to stick with carbonyls. Okay? And one of the main reasons we're going to stick with the carbonyls is that we do have this very, very slow step in the middle here. Okay? Well, one of the reasons it's favoring is that we can generate this phosphorus oxide as a product. If we didn't have a carbonyl, we don't have an electron-rich oxygen to help stabilize that phosphorus. We don't get the phosphorus oxide. We don't continue to see the pushing towards our products. Okay? So it is a reagent that is primarily driven for your carbonyl chemistry, because you really need that phosphorus oxide to help with that equilibrium. Okay? Questions about that? Okay. It's a nice overall reaction, just throwing this out. I know we're probably 3 weeks away from the exam, but it's a nice kind of neat reaction because you got substitution, you got elimination, and we have carbonyl chemistry in it. Okay? So it's something that you could very easily see shown on the exam as far as short answer going, telling me what types of reactions are occurring at each step. Yeah?
Because it's only one molecule coming out from phosphorus, we still not make that double bond.
The double bond has to do with the orbital overlap. Your oxygen still doesn't have, it's the same size as your carbon, so you're still going to have that odd orbital overlap. Okay. The oxygen is just going to do have more electrons, so it's better able to stabilize the phosphorus. Okay. Questions about our Wittig? Okay, we've got a few more slides on it, looking at individual pieces. So what you can go through and do is we can see how we connect two different carbon structures, okay, primarily through this double bond. Okay? So if we started with the red and the blue structure, and we wanted to force this reaction to occur, what reagents would we need to add? In theory, you all have awesome notes, then have exactly what those reagents would be. First step would be what? What's that going to react with? We don't have a CH3. We're not going to add CH3 in this case. CH3 was our general piece. Okay, what we said is that as long as we have a carbon with a leaving group, we can use any piece we want. What's the piece that we're going to use? There's our piece. So that's going to react first with our triphenylphosphine to generate this guy. What happens next? It's the next reagent we would need to add. What's that? We need to add that strong base. Remember, if we're doing any kind of Wittig, so if you see that triphenylphosphine or a carbonyl and a good leaving group, we really need to generate that strong nucleophile. To get the nucleophile, or a carbon nucleophile, we're going to have to remove a hydrogen. So our next step is going to be to add our really strong base. Butyl lithium does a good job of doing that. We end up with, at that point, I guess I can still attempt to color code this, just horribly. Triphenylphosphine, we have the negative charge on our carbon. That acid-base reaction works for two reasons. Actually, two reasons is a bit excessive. Our blue intermediate structure here has an issue with that positive charge on the phosphorus. We need to stabilize it somehow. What do we need to stabilize positive charge? Electrons. Okay? We don't want to exceed the octet on phosphorus. What we're going to have to do is bring on electrons from somewhere else within the structure. That's where our butyl lithium comes in, removes that hydrogen, and puts more electron density right next to our phosphorus. What do we now have? We have the carbanion, also known as our nucleophile. What does the nucleophile then do? Now it can react with our carbonyl. So we can go through that intramolecular four-membered ring to generate our new product. Okay. And technically, might as well attempt to go ahead and balance it. Our phosphorus oxide as well. Okay. When do you need to draw the phosphorus oxide? When you're asked for it. Okay. Very rarely will sapling ever ask for it. I don't think I will ever ask for it. Okay. Of course, I could be wrong in that, but I just don't see a particular reason to ask that. Okay. Questions about your Wittig? Got an example, seen a couple different ways to put it together and phrase it. What kind of leaving groups do we want? What's that? Did you say good ones? Halogens are going to be your good leaving groups. We're looking at bromine and iodine. You might also see chlorine. Okay. Did you really say good ones, or was there something else going on?
She said good ones.
Okay, no, that's fine. No, that's true. It is. Okay. So there's our overall mechanism where they went through and broke down all the individual pieces. Okay. We could look at it again if we wanted to do a retrosynthesis. So if you see that double bond, okay, if you see a carbon-carbon double bond in anything, not a bad idea to go through and say, hey, let's break that apart. and start from, do a Wittig reaction. So go ahead and split that to set up those possible reactants. Okay?
Is there any way to know what the leaving group is from just having the product at first?
That's what we just asked. What should the leaving group be?
Well, something good, but.
And these would be good. Our options for leaving groups, we need something good that limits the chemistry. There's really only one classification that does that, your halogens.
Well, I mean, we'll be able to tell if it's bromine or iodine.
So where you would see this kind of question is in a short answer. As long as you specified a halogen, you'd be fine. Okay. Probably the better leaving group would be best. So I would avoid chlorine, but bromine and iodine, good options. Okay. Questions about that? Okay, now what we're going to do is move into probably my least favorite, looking at water as a nucleophile. So this is ultimately oxygen acting as a nucleophile. Okay, so in general, what would we predict for water? Is that a strong or a weak nucleophile?
Weak.
Weak because? Okay, we could go with not wanting to give up its electrons. What else is a tip off that it's weak? Why is it stable? No charge. Okay? So look for that charge thing first. It doesn't always guarantee that you've got the correct setup, but hey, it's a good first step. Okay? So what's going to happen? We've got water, and we're saying now it is acting as a nucleophile, which means it is going to do what? I'll accept that. So we'll take our electrons and drive them towards the carbonyl carbon. We're now sharing electrons with that carbon. How many bonds does carbon now have?
5.
5. Can it have 5? Nope. So what happens? Break the pi bond. And we would generate our product from this. Let's see. Did I stepwise this? Yes. Our oxygen now lost electrons to the carbon, so it's going to become positive, or at least our water oxygen will. And then our carbonyl oxygen just gained electrons from the carbon. It's now negatively charged. Are we now stable? Nope. Why not? It's charged. Can we stabilize those charges? Yep. How do we do that? So we could go backwards, or we could try and remove a hydrogen by using some kind of base. That fixes our positive charge. How can we fix our negative charge?
Use an acid to
We could have some kind of acid floating around to pick that off. So what the next question was going to be, is it a good idea to now show in purple this mechanism? Why not? Why is it hard? You're absolutely right. Kind of like that. What's the transition state? How many atoms would be in the transition state? So we've got our oxygen forming a bond to the hydrogen, which is breaking a bond to that oxygen, which is bound to that carbon. How many atoms are in that? 4. We're back to that triphenylphosphine issue. Okay? We've got a four-membered transition state, which means the bond angles have to crunch down to 90 degrees to get that reaction to occur. Not a particularly likely scenario. It makes more sense to have the solvent act as your acid and base as necessary to go through and shift those hydrogens around. So that purple mechanism is probably the least valid of these. Okay? Which would mean on a test, what would I expect you to draw? Our red and blues. Okay? I don't want to see that purple one show up. Okay? That then pushes to our final product, and there we go. Okay? We now have this product. 2 names for this structure. For some reason, Sapling's calling it a gem-diol, and I'm going to guess that's because the textbook refers to it as a gem-diol. Gem stands for geminal, meaning the alcohols or whatever you're referring to are attached to the same carbon. Okay? So if we had a gem chloride or a gem halide, what we're saying is that those halogens are attached to the exact same carbon. Okay? And not positive on this, but I think geminal is also only referring to two things attached. Okay? More commonly, it's known as a hydrate. Why would we call it a hydrate? If you were dehydrated, you probably wouldn't be answering any questions. What does dehydration mean? Lost water. So what does it mean if you're hydrated? Added water. So when we're looking at this structure, we're typically referring to it as a hydrate because we've added water to the carbonyl. Okay? This reaction in general is pretty slow. Is there ways that we could speed it?
Would it make a difference if we decarbonate the water first and then?
So what you're suggesting is that instead of using water, we use OH minus. How is that going to speed up our reaction? Better nucleophile, which is a good thing. The other option, take a look at your product. In that first step, you wouldn't have the positive charge anymore. The hydrogen would already have been removed. So we can speed up our reaction by making the nucleophile better. Okay, a stronger nucleophile. What else could we do? What's the other thing that's causing that first step to be pretty slow?
The negative charge on the top oxygen.
Negative charge on the oxygen. How about we prevent that oxygen from getting that negative charge? How could we do that?
Protonate it ahead of time.
We could protonate it ahead of time. So that in our very first step, we'd have the OH. Is there an issue with this? Should see a pretty big issue. What's that?
You don't want the hydrogen and the OH reacting with each other.
Yeah. One mechanism, looking at affecting our nucleophile, we made it a strong base. The other version, by affecting our electrophile, was turning our making our electrophile more electrophilic by adding a strong acid. These are counteracting options. So we'll get potentially different results. We cannot do both of these simultaneously. We have to pick one or the other to see what the end result is. Which one do you guys want to look at first? Never mind, you don't get that question yet. Okay? So one of the things we can do is look at electrophile effects. Okay, we've addressed this kind of before with those first two. Okay, if we compare these two as far as reactivity, what functional group do we have? Top one is what functional group? Ketone. The next one? Aldehyde. Which one will we predict to react faster? Why the aldehyde reacting faster? So big one, steric hindrance. There is no steric hindrance in the aldehyde. We just have those hydrogens. So that's something that would help push that one to react faster. There's another thing that's helping that one react faster. We're looking at the electrophile. Which atom is the electrophile in both these cases? Our carbonyl carbon. What charge does our electrophile need to be? Positive. If it reacts faster, should it be more positive or less positive? Faster should be more positive. If we look at the difference between these two structures, we're looking at carbons versus hydrogens. Which one can stabilize a positive charge better? Carbons, because more electrons. Okay, they're bigger. So those can stabilize our carbonyl carbon. If we stabilize the carbonyl carbon, what does that do to its reactivity? Decreases it. We wouldn't expect it to react as fast. Okay? We're seeing a similar result when we go through and react it with water. The formaldehyde pushes almost entirely over to the hydrate form. Okay? That carbonyl carbon is very, very positive. Those hydrogens can't stabilize it hardly at all. And so it's really asking for that oxygen from our water to come in and stabilize that out and get that hydrate form. Whereas when we look at acetone, we don't see as much of a shift across. Okay, why? Because our electrophilic carbon is more stable. We've got those more carbons on those sides to help stabilize that electrophilic carbon. We don't see that reactivity. Okay? What happens when we move to the hexafluoroacetone? What's happening now? Which would we predict it to react similarly to, at least at first pass, formaldehyde or acetone? Probably the acetone. Why? Yeah, we're seeing more carbons there. We might expect a steric argument again, suggesting that we would get the same result as we get with the acetone. What ends up happening? It reacts similar to the formaldehyde. Why? We take a look at the other groups attached to those carbons. Those carbons have 3 fluorines on them each. Fluorine is much more electronegative than the carbon, draws the electron density away. Those carbons become very, very positive, which means they can't stabilize the carbonyl carbon. Okay? Again, water is going to have to come in to help stabilize that. Okay? So what we're trying to do is evaluate our primary differences first and slowly make it more and more difficult as we work our way through it. Okay? Start simple, make it more difficult. Also catalyzed by an acid. So this would be the question right here. You want to see the base or the acid catalyzed? Good guess. You wanted to see the acid. So if we're going to go through an acid catalyze this, we're going to start off by adding H+. Variety of ways we can add H+. Most commonly, you'll see it as H3O+ in this case. Why? What's one of the other reagents that we need for this reaction to work? Water. Okay, so if we're going to add H+ and water, we are effectively adding H3O+. When would we see just H+? When we don't want another nucleophile. Okay? So if there's no water present. Okay? Some subtle differences in how we discuss those. If we looked at our formaldehyde versus the H3O+, the very first analysis I would go through and do with it is the face test. Which are you more concerned about getting splashed in the face with? A nice strong acid or formaldehyde? You're not drinking it, by the way. Just don't add that layer of difficulty into this. Okay. Acid's a little bit more dangerous. Why? What about the hydrogens is reacting? Leaving's not the right word. What's the charge that builds on your hydrogens? H+, right? So the acid is reactive because of H+. What do we need to stabilize the H+? We need electrons. That's where we'll go to the formaldehyde, that oxygen, to share its electrons with the hydrogen. Okay? You'll notice that in this mechanism, they decided to use the lone pair. Why did they not use the pi bond? It's effectively the same, right? If we have this come out and react, we end up generating wow, extra carbons. Watch out for that. So we've got our positive charge there. After our first step, we end up with this guy. What's the relationship between these two structures? They're exactly the same thing. They're resonance structures of each other. The only difference is that we moved pi electrons down to form the double bond. Okay? So it doesn't really matter which version of the mechanism we use. I personally would probably push the pi, but the lone pair is just as valid. Okay? We generate that intermediate. That intermediate, through that resonance stabilization, puts a very large positive charge on our carbonyl carbon. The end result, we can get our nucleophilic attack. We need to stabilize that positive with the electrons from our oxygen. Come in, stabilize it. We generate, as we saw in our first version of the mechanism, again, our positively charged oxygen. We can go through another acid-base step to go ahead and remove that hydrogen. Okay, and we end up with our final hydrate product. First step. What type of reaction was the first step? Second step. Okay, we can look at it as a nucleophilic attack. Nucleophilic attack isn't really one of our reaction types, though. Yeah. We're looking at an addition. Okay, effectively the first step of an addition reaction. Last step. Again, acid-base. Okay. If you want to draw this all the way back to the addition reactions that you've seen before, almost all your addition reactions start with an acid-base reaction. So that very first step, we could actually classify as addition step 1. And the next one is addition step 2. Okay? So having an understanding of what types of reactions can or are occurring can help you go through and process what's happening within the mechanism. Okay? How is the acid speeding the reaction up? Good answer. It speeds it up by lowering the transition state, okay? Lowering the activation barrier for the reaction. That activation barrier is in that second step. Okay, right in here, our nucleophilic attack. How is it lowering the activation barrier for that step? Also a good answer. It is making the electrophile more electrophilic. Okay, our carbonyl carbon becomes more positive. It's now going to react faster. Okay? Does that make our product more favored? Kind of a tricky question. We sped up the reaction, so most people's gut instinct, if I speed it up, I get there faster, so that means I favor the product. No. That just means you get there faster. It also means you go backwards just as fast. Okay? So just because we add an acid does not mean we favor the product. It just means we get to the product a lot faster. So as far as a lab goes, we'll add acid catalysts all the time to speed up the reaction. That doesn't mean we get more product. Okay? How could we get more product? Kind of. You're actually, everybody's laughing, you're actually kind of right. What do you mean by add more reactant? I see two reactants. We've got the electrophile and the nucleophile. If you add more of each, no. If you add more of one of them, you can speed the reaction.
Did you get into like, so what is it? The pressure?
No, what did you start to say? It's Le Chatelier's principle. Okay, so this is also a big question when it comes to ACS tests, is looking at the activation barrier. Does it speed the reaction or does it change which direction is favored? But then also evaluate how can we make it favored. Okay, we can favor it by changing the concentration of one of our reactants. Okay? Or what we can do is start to remove products. What we're looking at there is Le Chatelier's principle. Okay? So our catalyst will just speed up the reaction by making more active electrophiles and nucleophiles. Does very little as far as favoring which direction you go. Okay? Questions about that mechanism? Okay. The other option, never mind. That is what I wanted to say. We're looking at affecting the nucleophile. To do this, instead of going under acidic conditions, we'll go under basic conditions. How do we know it's basic? COH minus. Okay, that negative charge is a tip-off that we've got both a strong nucleophile and potentially a strong base. Okay, so we'd start off our reaction again. Now with the stronger nucleophile, we don't need to activate our electrophile. The nucleophile attacks. Okay, at that point, we generate our unstable intermediate. Why is our intermediate unstable? The negative charge on our oxygen. How do we stabilize that? Protonate it. How do we protonate it? Why water and not acid? The acid would neutralize the base and we wouldn't have our strong nucleophile anymore. Okay? So when you're going through and looking at these mechanisms, one of the things that you'll typically see me go through and do is not specify what atom is pulling off hydrogens or putting on hydrogens. And that's because if it's under acidic conditions and I use a strong base by accident to pull off a hydrogen, my whole mechanism is now wrong. Whereas if I just say the hydrogen disappears, I'm fine. Okay? So kind of be aware of those limitations. Be careful on what you're putting in for each of those individual species. If we go through and identify again, what's happening in our first step of the reaction? First step? It's actually our addition. In fact, our nucleophilic addition just as before. Okay? It's a little bit different than our standard additions. Our standard additions, we almost always started it up with an acid-base reaction. Okay? In this case, we're doing a nucleophilic addition instead of the acid-base. The last step of the reaction, okay, we have our acid-base, or we could call it our addition step 2, or the second half of our addition reaction. Okay? So again, try and identify those pieces. Does the base catalyst make the product more favored? No, exact same reason the acid catalyst doesn't favor it. Okay? We're changing the activation barrier for an individual step, but we're not doing anything beyond that. It does not favor one over the other. Okay? Be aware of that when you look at your reactions. Next part of this is to address what are our nucleophiles. Okay, so in all of those cases we were looking at water as a nucleophile, but it doesn't have to be water. We could use an alcohol. How does the alcohol change the chemistry over water?
Stronger nucleophile.
What's that?
Stronger nucleophile.
If we had ROH versus H2O, we don't really have a stronger nucleophile. So we're looking at HOH or HOR. The nucleophile strength is pretty similar. We do see some adjustment, but not a lot. There is no difference. Mechanism is exactly the same. You're still pulling, either activating your electrophile by doing an acid catalyst, and we protonate our carbonyl carbon, or sorry, protonate our carbonyl oxygen, or we go under base catalyst, in which case we remove the hydrogen from our alcohol, and we generate our alkoxide. There's our strong nucleophile. So there is no effective difference as far as our mechanism goes. We get the exact same results. We've got our nucleophile, and we have our electrophile. The only thing that's slightly different is that instead of putting on hydrogens, we put on R groups. Okay? And we have the potential to put on 2. Whereas when we react with water, we don't really see a difference in our reaction. Okay? As far as which way does our equilibrium favor, we don't really have a huge favoring here. We'd go back to having to compare our aldehydes or ketones and try and decide what was going on there. We're starting with which functional group, at least in this drawing? Ketone. What did we say about our ketone favoring? Does it favor reactants or products? Our ketone was reactants because that carbonyl carbon is no longer as electrophilic. Okay? So if it's favoring reactants, how can we get our products to be favored? We could add more of one of the reactants. Which reactant do we choose? Okay. I personally would add the ROH, and there's a couple big reasons behind that. Any ideas why? I'm not sure I believe this one, but it's the one attacking. It's supplying the electrons. Okay? Since all of our arrows show the flow of electrons, it makes sense. If we put more electrons in, we should see a favoring. I don't quite believe that argument, though. Okay? The biggest reason? Probably cost. The alcohol is probably significantly cheaper than the carbonyl. So we'll put in more of the alcohol because it's cheaper. That's it. How else could we get it to speed up? Or sorry, not speed up, favor the products. We said we could put more of this guy in here. Pressure is an interesting one. With pressure, what's going on with that?
Put pressure on the reaction.
So we'll put pressure on the entire reaction. So you can't say we're just putting pressure on the reactants. That doesn't happen. So we put it on the whole reaction. What are we making an argument for? 152.
With more pressure, there's less volume, so it'll heat faster.
Not always. What's the difference you're looking at? Right idea. We've got 3 moles on one side, 2 moles on the other. So what happens if we reduce the volume? We reduce the volume, all of our molecules now want more space. So what are they going to do? They're going to start condensing to form into the 2 side. So we would favor the product. We're looking at a version of the Chatelier's principle. Everybody's favorite symbol, S, also known as entropy. Okay, it's a favoring based on entropy. Or we could adjust it as far as entropy goes by changing our volumes. Okay, if we look strictly at entropy though, which one would be favored? Left or right? Sorry, I did that one kind of backwards. If we shrink the volume, we're looking at Le Chatelier's principle, 3 versus 2. If we look at entropy, which side of the reaction is favored based on entropy? Entropy favors more disorder or less disorder? Entropy favors more things or less things? More things. Entropy favors our reactants. Okay. There's another method that we can go through and tweak. What else could we do? We could add more of one of our reactants, and we could also remove one of our products. Typically, we would remove water through distillation, but we could actually remove both the acetal and our water at the same time. Okay. As far as speeding it up, we can go back to our acid-base chemistry, exact same results as we had before. Okay. So, try to go through and draw this kind of pseudo-stepwise. We've got our carbonyl reacting with these 2 potential alcohols. You'll notice that this is not a complete mechanism. Okay, so first off, our first alcohol can come in and attack. So we've generated what's known as our hemiacetal, because we are halfway on the way to making a complete acetal. Our carbon is still extremely electrophilic in the middle. Why is it still electrophilic? Why are the electrons being pulled away from the carbon? We still have 2 oxygen bonds. Both those oxygen bonds are pulling electrons away from that carbon. Okay? That carbon is absolutely still electrophilic. Okay? So what can happen? Our other alcohol can come in and attack, and we can kick out water, and we've now reached the acetal form. Okay? What makes this fun? You're responsible for now knowing carbonyls, ketones, aldehydes, esters, all that fun stuff. Then you're responsible for looking at a structure and saying, is that a hemiacetal? Is that an acetal? How do we decide the difference? What's a hemiacetal have? Has the alcohol and the OR group. Okay? I believe it was you, Sean, that I was talking with about this. We have effectively an alcohol and an ether, sort of, with a carbon in common between them. Okay? With the acetal, what do we have?
2 R.
Effectively 2 ethers with our common carbon. Okay? So the reason I'm not saying 2 R groups, because I could have just as easily have come back over here and said RR. That has 2 R groups, right? Is that an acetal? No. Okay, so I want you to be a little bit careful with the statements. Okay? Yeah, I don't think I really want to step through all this. So what we could go through and do is make our nucleophile stronger by running under basic conditions. We can generate our hemiacetal just as we did before. Okay? Now the next thought is, can we push this to the acetal? Okay. If we're going to do the acetal, our strong nucleophile would need to come in, kick out, and we'd get our acetal. Okay, why is that last step not particularly likely?
You, I mean, I don't know.
All sorts of fun reasons on that one. Steric hindrance. Why would steric hindrance matter? Steric hindrance doesn't matter in an SN1 reaction, is what I'm getting at. Why does it matter here? Is it an SN1 step? What type of reaction occurred in that last step? It's SN2. In SN2, does sterics matter? Yes. In the SN2 mechanism, absolutely that's important. There's a lot of steric hindrance there. Well, why even push SN2? Maybe it's SN1. Why would we not expect SN1?
You have strong nucleophile.
Strong nucleophile, which would suggest we're looking at that SN2. The other thing that we could evaluate, what's the other product? OH minus. What can you tell me about OH minus? Yes, it is a nucleophile. What else can you tell me about it? As far as its leaving group ability. It's awful. Okay, it's one of the worst leaving groups we've got. Okay, so we've got steric hindrance being an issue. We've got a bad leaving group. Okay, this last step is just not very likely. So if we're going to run under based catalyst, we're probably going to stop at the hemiacetal. We're probably not going to be able to push all the way to the full-on acetal. Okay, all because that last step is not favored. So what happens if we went through and now adjust the electrophile? How do we adjust the electrophile? Did it with water. We'll run it under acidic conditions. So we can start with our acid. The acid is reactive because of that H+. Our electrons can shift. And we can go through, and I'll leave you guys to kind of do this, look at each of the individual products as we stepwise through it. At this point, we now have a reactive electrophile, so our nucleophile can then attack the electrophile, and we end up with an intermediate. What's the problem with this intermediate? Positively charged. How do we fix the positive charge? Where do we get electrons from? Yeah, we've got to get it from that oxygen-hydrogen bond. So we'll take the electrons out of that bond, give them to the oxygen. What do we pick up that hydrogen with? A base. So anything with electrons, we've got our alcohol also floating around in solution. This puts us to our hemiacetal. Okay? What happens once we've got the hemiacetal? We're still under acidic conditions. Okay, so what happens here? Our acid protonates again. We can protonate our alcohol. What's the big thing about doing that? We now have a really good leaving group in the water. That can now leave on its own. Okay? That gives us that carbocation intermediate. Okay, why is that carbocation intermediate stable? It's effectively tertiary. We could call it a secondary plus because we don't have 3 carbons. Now that we've got a pseudo-stable tertiary carbocation, we can permanently stabilize it with another attack from our alcohol. That alcohol is still not stable, so what can it do? We can take the hydrogen off using any random base that we had floating around in solution. How strong would that base be? Strong or weak?
Weak.
Why is it weak? It's under acidic conditions. So the base that we would have to use would have to be an alcohol floating around. Okay, we can't use anything strong. And then we'd end up finally with our acetal. Okay? So overall summary when we're looking at our acid reaction. So the far right-hand side is ultimately one of the things that you're going to need to look for. You need to be able to identify your starting carbonyl, the hemiacetal, and the acetal structures. Okay? As far as the summary goes, so I kind of want to get a little bit further. Our first step, we're looking at an acid base, or addition step 1. Next step is our addition step 2. Wow, that looks really sloppy. Addition, not much better, close enough. Then we've got an acid base, followed by an acid base. Leaving group leaves. Leaves begins with L in case you were curious. Then we have, whoops, a nucleophilic attack, followed by, again, acid base. Okay? Awesome. What's fun about this? It's not going to be fun to grade it. Right? This is a very common mechanism. I do expect you guys to know this one and be able to do it with new structures. Okay? The other thing that I would expect is for you to go through and label what type of reaction occurred in each of those steps. What's the acid? What's the base? What's the nucleophile? What's the electrophile? All of those are fair questions that I will ask. Okay? So that's your overall summary as far as your acid. Why do we not have a summary for the base catalyzed one? Can we make the acetal? No. The acetal doesn't work very well in our base catalyzed conditions. Okay? So let's crap. We'll go ahead and end with this slide. Okay? So let's go through and identify the following as hydrates. Next one. We're looking at the hemiacetal. Again, I'll try and highlight them all as we go through. Last one. None of the above. Let's go back to our acetals. What were the alcohol and the carbonyl? So what was the starting alcohol and the starting carbonyl? So this is a fun one. We're looking at a carbon-oxygen double bond and, OHs. Okay, and we want to know what's coming off of those. What I would go through and do is compare. Okay, if we look at the carbonyl, that's the one I would probably start with. The alcohol has a hydrogen on it. The issue with hydrogens, we can pull them on and off all day long, so that's not going to help us out. If we take a look at the carbonyl, we have a carbon that is connected to 2 oxygens. What carbon in our acetal is connected to 2 oxygens? Right here. So what is our carbon-oxygen bond? Those were the bonds we formed. So what we can go through and do, simplify out, right, and ethanol. So we got our pentane and ethanol. What happens with the middle one? This one's trickier. Where's our carbonyl carbon? Okay, it's going to be the one that looks most like a carbonyl carbon, one that has 2 carbon-oxygen bonds. So it's going to be this guy. We'll split these off. Doesn't have to look pretty, by the way. What is that carbonyl carbon attached to? Right? So we can go up. It's got some wings on it. That comes down, down, why is this one of particular interest? is an intramolecular acetal formation. Okay. Fun one, because most people like to split up the structure. You don't have pieces in this. It all occurs within it. As a very last check, we could count carbons. I see 1, 2, 3, 4, 5, 6, 7, 8 carbons. 2, 4, I see 7. Looks like I drew it wrong. Did I count wrong? Oh, I just counted wrong. Yeah, so it's 8. So we now have the starting material to make that acetal. Okay. Probably the trickiest one there. See what you guys can do to kind of match those. We've got officially 5 minutes before lab, so I'll go ahead and leave this up.